Hello and welcome to another episode of Maths with Mrs. Banks, where we make maths fun and easy to learn. And in this video, we're going to look at part 1 of 3 on trigonometric functions for mathematics grade 11, and that is the sine graph. On that note, please subscribe, like, share, and hit the notification bell so you don't miss out on part 2 and 3. Also, if you have any questions or would like to make a video request, please comment down below with the topic and grade you'd like me to cover that for, or alternatively send your questions and suggestions to the information provided in the description box. Now back to the video. In detail, we're going to look at number 1, functions of the form y equals to a sine theta plus q. That is revision from grade 10. I did a video on this. Please go check it out for mathematics grade 10 trigonometric functions part 1 sine graph. Number 2, we're going to look at functions of the form y equals to sine k theta. 3, functions of the form y equals to sine in bracket theta plus p. And lastly, we're going to look at how you sketch different graphs of the sine function. We have a lot to cover, so let's start. Overview from grade 10, y equals to a sine theta plus q. A deals with the amplitude. It tells you what the amplitude does, and q tells you what the graph does as you shift it up and down the y-axis. Now, the standard graph that we looked at is y equals to sine theta. That is an amplitude of 1, a range of -1 to 1 in terms of your y values, a period of 360 degrees, a maximum turning point at 90 degrees, and 1 minimum turning point at -1, 270 degrees, and -1. X-intercepts at 0, 180, and 360. Y-intercept at 0. Now, the effect of Q on the general graph is obviously shift up and down. If Q is positive, then you shift it that many units up. If Q is negative, you shift it that many units down. Effect of A, that affects the amplitude. If your A is 2, for example, in this case, your amplitude instead of being 1 becomes 2. And if your A is half, your amplitude becomes 1. If your A is -3, for example, your amplitude is still 3 because we're dealing with the absolute value here. The amplitude is the absolute value of your A. So, for example, in this case, we'll be dealing with the absolute value of -3, that is 3. So the amplitude will be a +3. So, but look at what the negative amplitude does to the graph. It flips it upside down. In other words, rotate it above the x-axis, meaning that instead of starting with a maximum turning point, you start with a minimum turning point and end with a maximum turning point instead of ending with a minimum turning point. In other words, you switch your turning points around. Now for the graphs that we basically are looking to study in grade 11, that is functions of the form y equals to sine k theta. What does k have an effect on the graph? What effect does k have? Basically, we're dealing with a period. It affects the period. How? The period becomes 360 degrees divided by the absolute value of k. Remember, absolute value makes any value, whether positive or negative, positive. So let's look at the standard graph y equals to sine theta. The period is 360 degrees, meaning we complete a period, a full cycle, with a maximum turning point and a minimum turning point between 0 and 360. It's a full cycle. Now, what happens when your k is any number besides 1? Because here it is 1. Let's say, for example, k is equals to 2. That means now your period has now changed from k 360 divided by 2. That gives you 180 degrees. That means instead of your graph finishing at 360 degrees, a complete cycle, that cycle is now completed in half the degrees required for the original one, meaning that in the end, the black graph, we end up with 2 complete cycles in a period of 360 degrees originally. When k is equals to half, you have only half of that graph. When k is equals to negative theta, what you do have is your period stays exactly the same, and you will see why. 360 degrees over absolute value of -1, that is equals to 360 over +1, which is equals to 360. All right, the period stays the same, but what happens to the graph or the function is that you achieve the same effect you would for negative sine theta. In other words, the amplitude of -1. So the graph gets reflected about the x-axis, it's flipped around. Instead of starting with a positive or a maximum turning point, you start with a minimum turning point and you end with a maximum turning point, and instead of ending with a minimum turning point. That's what happens. And then the period is obviously calculated as 360 degrees divided by the absolute value of k. Now let's look at the characteristics of y equals to sine k times theta. Your domain is an element of real numbers. There is no way along the x-axis where your graph is undefined. The range is between -1 and 1 because your amplitude is 1. And the reason why that is the case is because your a is equals to 1 here. The period is obviously 360 degrees divided by the absolute value of k. The y-intercept and the x-intercept in general, whenever you're dealing with graphs, functions, whether it is algebraic functions, your straight line graph, parabola, hyperbola, you name them. When you want to find the y-intercept, you make x 0. In this case, you make theta 0. When you want to find the x-intercepts, you make y 0. And then solve. That's generally how you would solve your intercepts in this. Now let's look at an example. Example 1. Sketch the following functions for your theta between -180 and 180 degrees. For each graph, determine the period, amplitude, domain, and range, x and y intercepts, maximum and minimum turning point. Now these are the functions: 3 theta, sine 3 theta, sine of theta over 3, sine of -2 theta, sine of 3 theta over 4. Notice that for each and every one of these functions, your amplitude, or your a in this case, is equals to 1. So the amplitude is the same. The domain and range are also the same. The domain is between -180 and 180. Your range is between -1 and 1 because your amplitude is 1. Now the period, intercepts, and the turning points are what differ depending on the graph you're looking at. Now let's calculate for each and every one of them right now. Let's go. All right, so now remember, with the standard graph of y equals to sine theta, you've got these critical points. The first one is your first intercept, which is at 0. The second one is your maximum turning point, which is at 90 degrees. The third one is your second x-intercept, which is at 180 degrees. And then you've got the minimum turning point, which is at 270 degrees. And then the last one is your last turning x-intercept, which is at 360 degrees. Remember, these are very important. So what you do is, whenever you're dealing with a function, does not matter what that function looks like, at the end of the day, what you do is, in order to figure out what the values for that function as, you take the angle 3 theta in this case, and you equate it to each and every one of these key points on the right hand side. So let's start. 3 theta equate to 0, therefore theta equals to 0. Okay, 3 theta equate to 90 degrees, therefore theta equals to 90 divided by 3, which is 30 degrees. 3 theta equate that to 180, Therefore, theta equals to 180 divided by 3, that is 60 degrees. Use a calculator just to make sure that you get your numbers right. 3 theta, equate that to 270 degrees. We get that, therefore, theta equals to 270 divided by 3, that is equals to 90 degrees. And the last one is 3 theta equated to 360 degrees. Therefore, theta gives you 360 divided by 3, that is 120. And now everything on the left hand side of this, you use your reflection to figure out, and then everything beyond to the right and to the left, you use periodicity to cover. So we're gonna start with 0, go to 30, go to 60, then go to 90, and then from 90 go to 120 degrees. Everything else we can just duplicate using periodicity and reflection and duplication. So now we're going to use the red color. So we go 0. Okay, we start at 0. Then the next one is 30 degrees. That is the maximum turning point. Then next 60 degrees, that's our 0. Minimum turning point is at negative 90 degrees, -1. And then we'll go back to 0 at 120 degrees. So what we do, beyond this to the right, we use periodicity. So we skip 1, 2, 3, 4, and then we have a point 1, 2, 3, 4, another point. We ended up with a minimum turning point, so we're going to have 1, 2, 3, 4, and then maximum turning point. 1, 2, 3, 4, 0. On the left hand side, we reflect like this. We started with a maximum turning point, so we must start on the left hand side with a minimum turning point at 30 degrees. Negative 30 degrees minimum turning point. That's how you reflect. Then 0 at negative 60. Maximum turning point at negative 90. Back to 0 at 120. Negative 120. 150 on the right hand side, we had a maximum turning point. So here we're going to have a minimum turning point at negative 150, and we go back to 0 at 150. Then we join the points. All right, let's join the points. There we join the points. Okay, let's fix that. On the left hand side, that's basically what the graph should look like. Now let's draw the next graph. The next graph is sine of theta over 3. And that gives us, okay, let's do the points, the critical points again. Critical points, important. Theta over 3 equate to 0. Therefore, theta equals to 0. Theta over 3 equate to 90 degrees. Therefore, theta equals to 90 times 3, which is equals to 90 times 3. That is equals to 270 degrees. But note that 270 degrees is out of the domain that we are dealing with in this particular situation, which is 180 degrees. So instead of forcing ourselves to calculate that, we find out what the graph does at half the point, which is 90 degrees. So we substitute that into the equation. That becomes 90 degrees divided by 3. Where there is theta, you just substitute the point on the x-axis where you want to see what the graph does. So you go sine. Make sure that your calculator is in DEG degrees, because then you will get the wrong answer, because it will be in either gradients or radians, and that is not really a wrong answer, but we're not using those types of measurements here. We're using degrees. So 0,5 at 90 degrees, and then at 180 degrees, that will be equals to, let's see, sine of 180 divided by 3, that is equals to 0,866, which is rounded off correct to decimals as 0,87. Now we plot. Okay, we plot. When we plot, it will be 0, and then that 90, 0,5, and then the last point as it goes. All right, let's plot. We're going to use a blue color this time around. Okay, blue, 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 blue. Okay, 0, and then at 90 degrees, 0, and then at 90 degrees, we have half. Let's make this thicker so that 90 degrees we've got half. And then at 180 degrees, that's 0,87, that's somewhere there. All right, same reflection on the other side. We had 90 degrees half, we should have negative 90 degrees minus half on the left hand side, and then the other negative 0,87. There it is. Now let's connect the points. Okay. Right, they're connected. Perfect. Next one, that is sine of minus 2 theta. Critical points, minus 2 theta equals to 0. Therefore, theta equals to 0. Minus 2 theta equals to 90. Therefore, theta equals to 90 divided by negative 2, which is negative 45 degrees. Negative 2 theta equals to 180. Therefore, theta equals to negative 90 degrees. Okay, negative 2 theta equals to 270. Therefore, theta equals to 270 divided by negative 2, that gives us 270 divided by negative 2, that is negative 135 degrees. The last one, negative 2 theta equals to 360. That means therefore theta equals to negative 180. Notice that we've got a negative k in this case. Negative k, remember, we switch the turning point. If we were to start with a positive 1 in the normal, then it means we'll start with a minimum 1. If we're supposed to start with a maximum, we'll switch to start with a minimum, and vice versa. Also notice that we're working on the negative. So on the negative degrees, right, we'll start with the maximum. We're supposed to start with the minimum. You will see as we plot. Okay, we're gonna use a different color. So here are the important points. The important points are 0, negative 45, negative 100, and negative 90, negative 135, and the last one is negative 180 degrees. So let's plot using the color green. So we're gonna use the color green on this one. All right, at 0 it's 0. At negative 45, okay, we've got a maximum. We're supposed to have a minimum in general. Supposed to have a minimum, but we'll start with a maximum at negative 45 degrees. Negative 45 maximum. And the next one is negative 90 degrees. That's a 0. Negative 90 degrees. That is an x-intercept. And then at negative 90 degrees minus 135 degrees, that is equal to a minimum turning point. And then we go back to 0 at negative 180 degrees. And then we reflect it on the right hand side. We started with a maximum turning point, so we'll start with a minimum turning point here at 45 degrees. Minimum turning point. And then we'll go back to 0 at 90 degrees. Maximum turning point at 135. Back to 0 at 180. All right, so now let's connect the points. There we go. All right, connect the points. There we go. That's how we connect the points. Next, the last one is sine of 3 theta divided by 4. Going back to black. Sine of 3 theta. 3 theta over 4 equals to 0. Therefore, theta equals to 0 times 4 over 3, so that's 0. Okay, 3 theta over 4. Therefore, theta equals to 90 times 4 over 3. Okay, 90 times 4 over 3. That's 90 times 4 over 3. Okay, which gives us what? 90 times 4 over 3. That gives us 120 degrees. That is a theta. Now let's go to the next one, 180. 3 theta over 4 equals to 180 degrees. Therefore, theta is equals to 180 times 4 over 3. And that is equals to 180 times 4 over 3. That is equals to 240 degrees, which is outside the range of this particular example, so we cross it off. What we do rather, however, is we find what the sine is at 180 degrees, the last bit. So we go sine of 3 times 180 divided by 4. That will give us what? Sine of 3 times 180 divided by 4. That is equals to 0,707, and so on and so forth. Now let's plot. So the crux is 0, 120, and that 0,7 at 180. 0, 120. So we're going to use a different color, that's purple. 0, 120, that's your maximum there. And then at the 180 mark, we've got 0,707. So that will be somewhere right under that blue one. On the left hand side, when we reflect, this is what we must have. we had 121, we must have negative 120 minus 1. Negative 120 minus 1, and then the last one will be round about just there. Now let's connect the two, all the points. Okay. And that's how you connect the graphs. Now we used a graph calculator, and this is what the graph calculator shows us. Okay, the purple one, that's y equals to 3 theta over 4. Let's compare it with the one that we drew. Correct. Green one, correct. That's correct. Red one also correct, and the blue one correct. Blue and red also correct. All these graphs are correct. Now next to the next question. Here we're given a question where they say find it for each graph of the form f of theta equals to sine k theta, determine the value of k. That should be easy. Remember, you can just count the number of periods you have, complete cycles you have in a 360-degree range, or you can use the formula. So you go find what the full period is. In this case, that's 180. Equate that to the formula. 180 equals to the formula for the period is 360 divided by the absolute value of k. Therefore, k is positive here because we start with a maximum turning point. So the k is positive. That is equals to 360 divided by 180. 180 goes into itself once and into 360 twice. So your k equals to 2. K equals to 2. You could have simply also counted the number of complete cycles in a 360 degrees. That's 1, 2. So your k is simple and straightforward here. The second question, though, however, is not so simple and straightforward. We have a situation where your graph starts with a minimum turning point, meaning that your k is negative. That's number 1. Number 2, your period is 270 degrees. That's where you have a full cycle. So what you do is you go 270 is equals to 360 divided by the absolute value of k. We know that our k is going to be negative because it starts with a minimum turning point. Very crucial. Now, therefore, absolute value of k equals to 360 over 270. Now, 90 degrees goes into 273 times and into 364 times. So, therefore, your k is equals to negative 4 over 3. Remember, because you start with a minimum turning point, so your k is negative. Therefore, your k equals to negative 4 over 3. And that is how you answer questions like this. Next. Let's look now at the functions of the form y equals to sine in bracket theta plus p. Now, what is the effect of p on the graph? To cut it all short, the effect of p is basically a shift along the x-axis. Positive p means you're shifting to the left. Minus p means you're shifting to the right. For example, the standard format is y equals to sine theta. That's the red graph. There is no shifting here. You have a period of 360 degrees between 0 and 360 degrees. Now, what happens is that the blue graph, we've shifted this graph 90 degrees to the right because there is a minus in front of 90 degrees. How? Let's see. Originally, the red graph starts with a peak at 90 degrees, right? Look at the peak of the blue graph. It's at 180 degrees, which is 90 plus 90. So we shifted it 90 degrees to the right. The graph of red, y equals to sine theta, starts at 0 degrees at the origin. The graph of this one starts at 90 degrees. And you can continue comparing. Now let's look at the green graph, y equals to sine theta in bracket theta plus 90 degrees. This one, you're supposed to be shifting 90 degrees to the left. Let's see. With the red graph, which is not shifted, the maximum turning point is at 90 degrees. Now with the green graph, it's at 0 degrees. So meaning you shifted it 90 degrees to the left. Also, the graph of y equals to sine theta starts at 0. This one, the green graph, starts at negative 90 degrees and then goes to 90 degrees. That is the first intercept on the positive side. Same thing, y equals to sine of, in bracket, theta plus 180 degrees. That is shifting the graph 180 degrees to the left. Remember, plus p to the left. So that means, okay, let's compare. We started with this one. Now when we shift it 100 degrees to the left, that means we jump 90 to 0 and then another 90 to negative 90 degrees. That's what happens. Now let's look at some examples. Example 3. Sketch the following functions on the same set of x64. Theta is between negative 360 and 360 degrees. You've got the standard sine graph and then the one that is shifted 30 degrees to the right because we've got a minus. Remember, minus p means to the right. Plus p means to the left. Remember that. Always keep that in mind. Now determine for each of the following: the period, amplitude, domain, and range, x and y intercept, maximum and minimum turning points. Now let's look at what is common. A for both is 1, so the amplitude is 1 for both of them. The domain and range is also common. Domain is between negative 360 and 360, and the range is between negative 1 and 1 because your amplitude is 1. Now where they differ is with the x and y intercept and the maximum and minimum turning points. Let's see what we get there. Let's plot the standard one, y equals to sine theta. That should be easy because we've been plotting that for quite a bit now. So let's go. Let's plot the points. So we start at 0 and then go 90 degrees. Let's count. 30, 60, 90. That is the maximum turning point. 1 to 3. That is 0. 180. 1 to 3. That is the minimum turning point. 1, 2, 3. And that is back to 0. On the left hand side, we reflect. Here we started with a maximum turning point at 90 degrees. We must have a minimum turning point at negative 90 degrees. So we go 1, 2, 3. Let's count. 1, 2, 3, minimum turning point. That's where it should be. 1, 2, 3, 0. 1, 2, 3, maximum turning point. 1, 2, 3, 0. Now we connect the points, we join the dots. Okay, on the left hand side as well. Now let's draw the graph of y equals to sine theta minus 30 degrees. Remember, we just shift that to the right 30 degrees. So let's use a blue ink here. Blue. So what happens is that we just move everything or shift everything 30 degrees to the right. So instead of starting at 0, we start at 30 degrees to the right. Everything, maximum turning point 30 degrees to the right. 0, 30 degrees to the right. Minimum turning point 30 degrees to the right. The last bit would have been here at 390 degrees, but we don't have that in the range. So what we're going to do is we're going to calculate what the sine of 360 degrees minus 30 is over there. So let's reflect the graph on the left hand side. We started with, okay, so we're going to go 30 degrees to the right of this point. 30 degrees to the right of that, 30 degrees to the right of this, 30 degrees to the right of the last one. Now on the negative 360, we need to calculate what that is. Let's start with the right hand side. Let's calculate what the graph does at 360 degrees. Let me reduce the size of this. It's too big. So we go sine of 360 minus 30 degrees. We go sine of 360 minus 30, that is equals to negative 0,5. All right, so we go to the graph and we plot negative 0,5 on the right hand side. Okay, we'll plot that. Let's remove this first so we can plot the point. So that is negative 0,5 on the left hand side. There. Sorry. Let's be precise. On the left hand side, we go sine of, take out a calculate, sine of negative 360 minus 30. That will give you negative 0,5 also. So that's where it is. Now we connect. We join the points. Before we do, let's figure out what the y-intercept is going to be, because now that we've shifted, the y-intercept will obviously change. To calculate the y-intercept, all we need to do is make x 0. So let's make x 0. So let's make theta 0. That means sine of, instead of theta, we go 0 minus 30. So we go sine of 0 minus 30 equals to, that gives us negative 0,5, and that is that point on the y-axis. So remove that so we can draw the graph without interruptions. Now let's join the points. Right. Let's join the left hand side. All right, and then the last bit we join like that. Now let's check out what the graph looks like. The graphs look like on a graph calculator. Perfect. Excellent. Compare. Correct. Now, next question. Sketch the graph of f of theta equals to sine 45 degrees minus theta. We never dealt with this. All the time we've been dealing with theta coming first and not the angle. So what we do now is we'll rearrange that. That should be easy. It shouldn't be an issue. So you rearrange that so that becomes y equals to sine of 45 minus theta. That is equals to sine of, so you put a negative sign in front of all that, so you change everything around, you arrange. You're not essentially changing anything. Let's look at it. That is still minus theta, and that is still positive 45. So that becomes negative sine of theta minus 45y, because sine of negative theta in general is equals to minus sine theta. Keep that in mind. Now that is equals to, so now what we do is we keep in mind that this is a negative one. So where there was a maximum turning point, it will be a minimum turning point. Where there's a minimum turning point, it will turn into a maximum turning point. Notice also that we've shifted this graph 45 degrees to the right. It's minus, so it's shifted to the right. But where there is a maximum, it's a minimum. We flipped it upside down. Let's first draw the graph of y equals to sine theta to get perspective. So we'll start with that. So that's between 0 and 360 degrees. So at 0, that's 0. At 90, that's 1. At 180, that is 0. And then at minus 270, that's negative 1. Then at 360, that is 0. That is 0 again. Okay, let's just double check. Okay, that is 90 degrees. That is 270 degrees. 360 degrees. 315, 30, 45, 60. Right, there is 360. All right, so we join. No, that is not 180. 180 is here. This is on 15 degrees. That's how the sine graph turns out. Now we draw the sine of negative theta minus 45. Remember, let's deal with the 0 points first. Okay, so where it starts at 0, we start at 45. All right, that is 15, 30, 45. Okay, so that is 45. That's where we start. It's our 0. Sorry about that, 45. And then now we should have a maximum turning point at 90 degrees plus 45. 90 plus 45, that is 135. We should have a maximum here at 135. But remember, it's the other way around. We have a minimum turning point here. So we go there. We should also have a 0. Okay, so we count 45 and we will have a 0. 45 after 180. 45 after 180. 180 plus 45, that gives us 225. So we have a 0 there. Okay, we should have a minimum here at 270 plus 45. 270 plus 45, let's see what that gives us. 315. We should have a minimum at 315 under normal circumstances, but we will have a maximum there. So there we have a maximum. And then we will have to calculate what we get at 360 degrees. So we go minus sine 360 minus 45. Okay, so we go negative sine in bracket 360 minus 45. That gives us 0,707. So that will be somewhere there, 0,707. All right. And then on the y-intercept, we make theta 0. So that will be minus sine in bracket 0 minus 45. That gives you 0,70. So that is along the same line as this one. So we get it to the other side and that's where we put it. Now we join. Join the points. Let's start with the ones. Alright. Now this one becomes that. Alright. Now let's check out what the graph calculator calls us. So this is the shifted graph, and that is correct and excellent. Just double check again. Excellent, correct. Now for the last question, we have f of theta. Sketch the graph of f of theta equals to sine theta plus 60 degrees for between 0 and 180 degrees. First, notice that these are multiples of each other, so what you do is you factorize. So let's factorize that. Let's go. Y equals to sine of, take out a common factor 3, you're left with theta plus 20. And now things look so much clearer. So we've got a period of 360 over 3, which is equals to 120 degrees. And that was shifted 20 degrees to the left because it's plus 20. So now we can draw the original graph, but let's see what the important indicators are in this case. Remember your zeros and what. Let's now compare equals to 0. Therefore, theta plus 20 equals to 0, meaning that therefore theta equals to -20. This is outside the range, so we're not going to include it. What we're going to do on the other hand is you find the y-intercept. The y-intercept, right, is at the point where your theta is equals to 0. So we find that sine of 3 times 0 plus 60. In other words, sine of 60, which is equals to, okay, sine of 60, and that is equals to 0,866. So that is 0,87. That is the y-intercept. Now let's find out what we have at 90 degrees. Okay, 3 theta plus 20 at 90 degrees. That is equals to theta plus 20 equals to 90 degrees divided by 3, that is 30. Therefore, theta equals to 30 minus 20, that is 10 degrees. All right. Let's find out what happens at 180 degrees. 180 degrees. Let's find out what happens at 180 degrees. 3 in brackets theta plus 20 at 180 degrees. Therefore, theta plus 20 equals to 180 divided by 3. That is 60 degrees. Therefore, theta equals to 60 minus 20, that is 40 degrees. Okay, at 270 degrees, theta plus 20 equals to 270 divided by 3, that is equals to 90 degrees. Therefore, theta equals to 90 minus 20, which is 70 degrees. Then on the last one, 360 degrees. 360 degrees. Therefore, theta plus 20 is equals to 360 divided by 3, that's 120. Now, therefore, theta equals to 120 minus 20, and that is 100. So we're done with the last one. Now, what we're going to do is everything we're going to use periodicity to duplicate and continue. So let's go. The first one is that we need to think of is 0. Okay, we've got 10. So we've got 10, and then 40, then 70, then 120. No, 100. All right. So we've got 10. Okay, first let's plot a normal sine graph, and then we'll plot this one in red, normal sine graph in red. Okay, that's 0 at 0, and then at 90 degrees, that's your maximum turning point, and it goes back to 0 at 180 degrees. And let's connect. That's what the normal graph of sine theta does between 0 and 180 degrees. Now let's plot the other one. It starts at 0. It starts at 10 degrees. That's at 10 degrees. That's your 0. Let's see, what is 10 degrees? Again, degrees, that is your maximum turning point. 10 degrees maximum turning point. Then you've got 40 degrees, which is your 0. 10 degrees maximum turning point. There. Then a 0 at 40. Next is 70 degrees. That's your minimum turning point. Okay, minimum turning point at 70 degrees. Minimum turning point, and then it goes back to 0 at 100. And then we duplicate from then on. Now let's count how many we must skip. We must skip 2, 4, 6. Okay, 2, 4, 6, we have a maximum turning point. And then again another 2, 4, 6. Let's see, 2, 4, 6, that's a 0. 2, 4, 6, that's a 0 at 160 degrees. And then let's see what it does at 180 degrees. Okay, let's see what it does at 180 degrees. Okay, at the origin, or the y-intercept is 0.87. Okay, let's play that one. 0.87, 0.87. Wait, that's somewhere here. Now at 180 degrees, that's let's sign off in brackets. Let's go back. Sign off in bracket. 3 times 180 degrees plus 60, and that gives you minus 0.866, which is negative 0.87, negative 0.87. That should be somewhere here, negative 0.87. That is somewhere here. Now let's join. Let's connect the points. That's how they should connect. Now let's check out the graph that was calculated by a machine, the calculator, and that is excellent. They all match. That is the end of the video. Thank you very much for watching. See you in the next video. Bye.